Hello, Mr. Simpson here with our video for 10.3 phase transitions. You can see the learning objectives here. One of the learning objectives as listed in the textbook I've actually put into the video for 10.4, so you'll see that in the next video. Please pause the video to copy these in your notes. All right, so we start with understanding what the phase transitions are, and here I've listed those phase transitions, and we'll be able to see this graphically even more when we look at a heating curve and also a phase diagram. But we basically have three phase transitions here, so vaporization and condensation. So this is the phase transition between liquid and gas. Okay, where going in one direction, liquid to gas is vaporization, and going in the other direction, gas to liquid is condensation. Okay, melting and freezing is the phase transition between the states of liquid and solid. Okay, and the sublimation deposition is the between solid and gas. Okay, so in each of those cases, in going in one direction from one to the other, liquid to solid is freezing, solid to liquid is melting. All right, so let's take a little deeper look into some of these terms and some of these phase transitions, and we'll start with vaporization. Okay, so this is a liquid converted to a gas. So this actually can occur in a couple ways. So first, we can think of this happening in an open container. All right, so if you leave a glass of water on the counter over time, the liquid will change to vapor to the point where all of the liquid has evaporated into the vapor or gaseous state. Okay, it's a little different if we think of this in a closed container. Okay, so we don't get that complete transfer of liquid to solid because it's a closed container. So what actually happens is we get an equilibrium between the liquid and vapor states. Well, what does that mean, equilibrium? So that basically tells us, so what is happening here in a closed container is we reach a certain point where we have a dynamic equilibrium, in which case the liquid level doesn't change. Okay, so the liquid level does not change. That means that the number of gas molecules doesn't change. And so if the number of gas molecules remains constant, because the liquid level is not changing when we reach this point of equilibrium, therefore we have the pressure exerted by that vapor over the liquid remains constant. And this value is an important one for us. This is the vapor pressure. So we've referenced this before, vapor pressure. And so that's where it comes from. So in a closed container, the liquid molecules are escaping to the gas phase, but at some point we reach this balance equilibrium where the liquid molecules escaping the gas phase and the gas molecules returning to the liquid phase, so that evaporation condensation that is happening reaches a dynamic equilibrium, where at this point the liquid level doesn't change anymore, the number of gas molecules doesn't change, and because the number of gas molecules remain constant, we can calculate or we can determine this concept of vapor pressure. We referenced vapor pressure when we talked about intermolecular forces. So vapor pressure is definitely going to be affected by two things: the intermolecular forces present. So the stronger the intermolecular forces, the harder it will be for liquid molecules to change to the gaseous state. And the other thing, obviously, is temperature. Okay, so if I increase the temperature, then the intermolecular forces will break faster and more often, and so we will get more molecules into the gas state, so the vapor pressure will increase. This vapor pressure actually ties into a physical property that we're more familiar with, and that is boiling point. So you can see here that the relationship between vapor pressure and boiling point, The temperature at which a liquid boils depends on the pressure above it. You may be familiar with this. For example, if you're at a higher altitude, the last point on here, because you're at a higher altitude, the atmospheric pressure is lower, so the boiling point is lower. So there's a direct relationship between how pressure and affects the boiling point or that change of state. So a couple key takeaways here. When the vapor pressure of a liquid increases enough to equal the external atmospheric pressure, this is when the liquid reaches its boiling point. Okay, so when we talk about the normal boiling point of a liquid, it's the temperature at which it boils at 1 atmosphere, that standard pressure value. And then this is a key concept that we'll take a look at in the next video when we look at the heating and cooling curve. So this relationship between vapor pressure and temperature is mathematically represented by the Clausius-Clapeyron equation, which you see here. Okay, so this talks about or shows us the relationship between those pressure values, and the temperatures at which the substance. So that we talked about that the vapor pressure is going to be affected by the temperature. So as the temperature change, that value is going to change too. You can see here that I also have to take into account the gas constant. Okay, so because I'm talking about gases and pressures, so I've taken into account the gas constant, and we're adding heat or removing heat if we're going the other way. So there is this enthalpy of vaporization, this heat of vaporization that occurs whenever I'm changing those values. So I have to take that into account with each of these. And you can see that, as always, when I'm using constants, I have to be careful of my units. Okay, so here is an example problem. So take a second to pause the video and copy this in your notes, and then I will kind of work through it with you. All right, the good news is the wording here is pretty straightforward. So it's certainly a function of kind of plug and chug work. But we need to make sure that our units match up, and also we get all the information in the proper location. Since we have 2 pressures and 2 temperatures, obviously if I put those in the wrong spot, I'm going to end up with the wrong answer. Okay, so as I read this, at 20 degrees Celsius, the vapor pressure of ethanol. So here, this temperature and this vapor pressure go together. Okay, so if we want to call those P1 and T1, we can put 5.95 kilopascals down here, and I can go ahead and fill in my R value, and I can put my first temperature. Now, because of our R value, just again, is joules per mole Kelvin, so our temperature values need to be in Kelvin. Okay, so let me go ahead and put this in here, joules per mole Kelvin, so that I know that my temperature values need to be in Kelvin. So 20 plus 273.15 gives me 293.15. Okay, now I can fill in my other pressure and temperature. So there are my P2 and T2. So pressure of 53.3 kilopascals and a temperature of 63.5 plus 273.15, 336.65. Okay, so now it's a lot of math here to solve this out. I actually try to break this down into smaller steps. I'll kind of show you how I work through this here. So I do the math inside these brackets first with my temperatures. So 1 divided by those values, I get 0.003411 minus 0.002970. So I get a value here of 4.41 times 10 to the negative 4th. You can check your work to make sure you're getting that same value there. If I divide over here my 53.3 divided by 5.95, and then take the natural log of that, I get 2.19. Okay, so now to solve there, I would, I can multiply by the 8.314, and I get 18.2 equals my heat of vaporization times that 4.41 times 10 to the negative fourth value. And so now I can solve for my heat of vaporization. I get 41,300. This would be joules per mole or joules. Obviously, a number that big, I would typically write it in 41.3 kilojoules or kilojoules per mole. Okay, so we'll have some practice. Obviously, since this equation is plug and chug, in this particular example, we were asked to solve for the heat of vaporization. I could be asked to solve for, either one of the pressures or either one of the temperature values, and I would just have to make sure I could manipulate this equation to solve for the unknown given the other pieces of information. All right, that wraps up this video on phase transitions. In our next video, we will look at heating curves and phase diagrams.